Next speaker is Galen McKinley. She's going to talk to us about detection of change in ocean carbon uptake from both data and models.
Thank you, Nikki. And I'm very much going to follow on the great talk from Peter and talk about kind of what I would say is the next step. How do we move beyond understanding just that internal variability and really quantify it in comparison to the force change, the change that's due to increasing atmospheric PCO2. But really the key thing there is that there's all this internal variability out there in the ocean carbon sink, and we need to separate those pieces. But to begin with, I want to thank the people who've been working on this with me for a long time, Amanda Fay and Darren Pilcher and the rest of my research group at Wisconsin, Nikki Levenduski at UC Boulder, Matt Long and Keith Lindsay at NCAR, and of course the funding. Thank you to NASA and NSF for funding this research. And my take-home message is, it's always good to start with the end, in case I don't get quite to the end. I want to begin by convincing you that since pre-industrial times, cumulatively, the ocean is the only sink for anthropogenic carbon from the atmosphere. That's a slightly different story than if you just look at the last decade, but when you accumulate, it's only the ocean that's been a sink since pre-industrial times. As atmospheric PCO2 increases, we should expect this sink to be growing, and the evidence we have suggests a growing sink, but there's a lot of uncertainty in those estimates, and that means that direct detection of growth in the carbon sink is really not yet possible due to internal variability as well as data sparsity that Peter talked a lot about as well. Those are real challenges to directly seeing where and how much the sink is growing over time. And so this leads to a desire to really understand when we're going to see growth in the carbon sink. When and where do we think we're going to be able to detect this first? And for this, we're going to need an Earth system model to ask this question. And the big picture here is that, of course, understanding the carbon cycle is key to diagnosing and predicting climate change. We know what's driving this increase, and we know that the land and the ocean are modulating this. And we need to understand how the ocean carbon sink is evolving, because it's a critical part of going, as this goes forward, how much climate change is going to occur depends a lot on how much carbon the ocean will take up. So to begin with, we want to look at this from the observation standpoint. And I'm going to take two perspectives. One, looking at column integrated anthropogenic carbon accumulation, which is really our best solid estimate of how much carbon the ocean has taken up over time, based on the Woest-Jagoff survey and the continuing GOSHIP and CO2 CLIVAR. And then I'm also going to talk about surface air-sea fluxes. And one separation between those two that I need to start out with is the fact that in the ocean, the total carbon concentration of, say, the surface ocean is only about 3% anthropogenic carbon, this perturbation that we're interested in, while about 97% is the natural carbon cycle. And of course, we all know when you're looking for a needle in the proverbial haystack, that creates challenges. So that's just one thing I'll start out with. And then when we're looking at this column integrated view, we really are trying to directly look only at the anthropogenic part. And over here, we're largely looking at the total flux. So that's the key reason why these two maps look so different. I should tell you what the maps are. This map is in moles per meter squared, the column integrated surface to depth of the ocean concentration of anthropogenic carbon in the ocean in 1994. You can see that at that point in time and continuing to this day, most of the anthropogenic carbon, or the most intense column integrated values of anthropogenic carbon, are in the North Atlantic and in the intermediate waters of the Southern Ocean, while the rest of the ocean has a lot less anthropogenic carbon in it in that column integrated sense. And this is really a hallmark of the overturning circulation of the ocean. The newest waters in the ocean, those that have most recently seen the atmosphere, are in the North Atlantic and in the intermediate waters of the Southern Ocean. This map tells us about the annual cycling of carbon between the ocean and the atmosphere, with outgassing in the low latitudes primarily and uptake at the higher latitudes, and of course this complicated pattern in the Southern Ocean. And this is from Peter's recent paper. Okay, so to begin with, I'm going to talk about anthropogenic carbon and how this allows us to say that the ocean is the only sink since pre-industrial times for anthropogenic carbon from the atmosphere. How do we get this information? Well, people go out on research ships and take water and do really high quality observations and build up these really high quality sections, I'll say along A16, of the total carbon in the ocean, also observing oxygen, CFCs, a whole bunch of other tracers. And they do this, we've done this with the Wells-Jagosz program in the 1990s, continuing with CO2 repeat hydrography and now GoShip to reoccupy these lines. And what this led to for the first time in around 2000 was this three-dimensional picture of where carbon is in the ocean, as well as oxygen and CFCs and other things with which one can back out in complicated and ways and challenging ways, but came up with good estimates of how much of that carbon in the ocean was only due to human activities. What carbon is in the ocean that wouldn't be there if humans hadn't put carbon in the atmosphere. And that leads to this map that was first put out by Sabine et al. 2004. We're using multiple tracers. They estimated this concentration of anthropogenic carbon in the ocean. Here's that column integrated picture, and here are sections in the Atlantic, the Pacific, and the Indian. You can see that the anthropogenic carbon is primarily in the surface ocean and in the bowls of the subtropical gyres, and only in the Atlantic has it penetrated below about 2,000 meters into the deep ocean, thus leading again to this bullseye. So this was really groundbreaking that we could do this. We could now close the global carbon budget by saying how much carbon was in the ocean with about 10% uncertainty or so. And that allows us to say, well, how much, if we take the residual from what went into the atmosphere, what we find in the atmosphere, we can estimate the land, how much has gone into the land. But the challenge with this, what this didn't provide was a time history. How did we get here? How did this sink proceed over time? And so that was essentially the next step, was to say, well, if this is where we were in 1994, how do we get here? How did the ocean take this carbon in? And so that led people like Samar Katiwala and others to develop modeling techniques that would allow you to essentially propagate this signal, estimated for 1994, into the ocean and give us this time history here back to 1765 of where carbon went into the ocean. Now, the challenge with those models is that they don't, of course, have resolution of how the ocean circulated or what the biology was back over that time. So they had to assume constant circulation and biology in order to get this. And that's the major uncertainty here, is that assumption of constant circulation and biology. And that leads to much of their uncertainty estimate here. But still, having this allows us to combine the information of the ocean sink over time with the fossil fuel emissions and the atmospheric reservoirs from ice cores, and then direct observations. And that allows us to back out then the land sink over time, or more properly said, the land source over time. So you'll see from here, and this is taken by direct difference, and the uncertainty here is just accumulation of these uncertainties, and it is a much smaller uncertainty than any direct estimates out there of the land use source or of the terrestrial sink. Those, if you take those estimates, they span up and down here. So this is our best constraint on what the land must have done over the last 250 years here. A source of carbon through about World War II, and then a turning around and becoming towards a sink, but still the ocean has been a source over time. I'll show you that with these other plots. Oh, and I'll mention that these are the graphics that are available from the OCB website, so you're welcome to use them in all of your presentations and teaching. Okay, so another way to look at that are these bar plots, sources and sinks between here 1900, 1955, and 2011. You can see that in 1900, the land was the dominant source. 55, fossil fuels and land are about equal. And then 2011, the fossil fuels are clearly the dominant source. But that net sink, our best estimate is still, it's a source. All right? So this is where I'm trying to convince you that the ocean is the only sink cumulatively over time for anthropogenic carbon. And I hope this is a message we'll all get out there as we give our own talks and education. The ocean sink is really critical because it's all that's damping the rate of global warming to date. And then going forward, if we take model projections here with 2016 here, going out to 2300 with the NCAR climate model from Randerson et al. 2015, we see that we're predicting with a high emission scenario a continued growth in this sink, so that we are expecting this sink to continue to modulate our global warming. So it's pretty important to understand how it's going to be evolving over time. And we're expecting it to grow over time, of course. But of course, our models aren't perfect. And we know that the ocean circulation is not constant over time, nor is the ocean biology constant over time. And so we really need to ask ourselves, is the CO2 sink actually growing as expected? Are we really seeing this? And to do that, we don't have enough hydrographic observations to do that directly. So I'm going to turn to the same observations that Peter's been using to ask this question from the perspective of the surface flux. Now this is a map of, similar map to what Peter showed, this is the Lamont database here, again showing the heterogeneity of the observations of surface ocean PCO2. And that's a real challenge we have to contend with. And again, as Peter said, the CO2 flux is proportional to the delta PCO2. So I'm just going to focus on PCO2 for this part of the talk and the delta PCO2. Okay, the basic idea here, I'll explain in a couple slides, is that essentially if the atmospheric CO2 is growing and the ocean is sort of passively responding to that, not changing, and just sort of responding kind of like a passive reservoir, the delta PCO2 of the ocean would be constant over time. And since the CO2 flux is proportional to that delta PCO2, if you have no change in the delta PCO2, you'd have no change in the flux. And so that would be an indication of steady sources and sinks in some part of the ocean if you were to observe a PCO2 of the ocean going up at the same rate as the atmosphere. The corollary to this is that if the ocean PCO2 is going up more rapidly than the atmosphere, the delta is declining. If the PCO2 of the ocean is going up more slowly than the atmosphere, the delta PCO2 is increasing over time, and therefore you'd have a declining sink in the red case and a growing sink in the blue case. And so if you go out into the ocean and you observe this, then that would be evidence for that growing sink that these other methods, the interior methods, the models are suggesting we should be seeing. So that's really the signal that we're looking for. We're going to use the LDO database here to look at these trends over large-scale biomes of the global ocean. So these biomes are fixed in time. They're based on chlorophyll, mixed layer depth, and SST. And we're essentially aggregating the available observations in any one of these biomes to a single time series representative of that biome and asking the question, how is the trend in that biome comparing to the atmosphere? These are the kind of data we might have for a particular biome, say for the subtropical gyre of the North Atlantic. You can see that even though we're aggregating over a very large region, a region that's of the better sampled of the world, there's a lot of gaps in here. And so essentially what we're doing is we're saying we have some observations that we are taking into account the background large-scale distribution of PCO2 to collapse them to a single time series, calculating a biome monthly mean, and then simply fitting a linear trend and a harmonic to that. And then it's the slope of the blue and the slope of the red that we're comparing to say whether the ocean PCO2 is going up more quickly or slowly or at the same rate as the atmosphere. Okay, so these are the kinds of results we can get from this. Again, red is declining sink, blue is a growing sink. Here's for 1990 to 05, and here's 81 to 2010. So this is sort of a decadal and multi-decadal time frame. And you can see that if we just look at this decadal time frame, we see red indicating a declining sink, blue indicating a growing sink, and pink indicating a sink that's not changing over time or a constant sink. And that if we look at a longer period, it's very different in most of the biomes. And I'll also note that when we're slashing out here, it indicates that we probably don't have enough data for that particular time frame. So we're focusing on the regions that aren't slashed out. So even the regions that aren't slashed out, we see on the long term trends that are either neutral or perhaps growing. But what's not really clear here is what is the transition between one to the other? When are you really going to see that response to the atmosphere? The fact that these are so different suggests that this is probably affected by internal variability, natural variability in the climate system. Is this a long-term response remains a question. So the first thing we want to do is say really on what time scale is all this variability kind of going to wash out? How do we look at all these different maps Should we make these maps 180 different times to cover all the potential time frames within this time series? And what we do is we say, well, let's just take a brute force approach and look at all these time series that are available between the 80s and 90s and the 2000s and map them up all at once and look at how the trends change depending on if you change your starting and end points. And so that leads us to these grids where we have start years on the vertical axis, end years on the horizontal axis. So these are 3-year time series, these are 29-year time series, and the jagged lines are 15, 20, and 25-year time series. So the point is we're looking at all the time series available from that data set that I showed you on the previous slide and asking when does the trends kind of start to follow a consistent pattern. And also on here I'm showing when you have warming trend in any of the time series that also goes with PCO2. Okay, so for the subtropical gyre, we see that after about 20 years, we pretty consistently see pink, or trends in the ocean PCO2 that are consistent with trends in the atmosphere, or a steady sink. But if I look at a different biome, say the North Atlantic subpolar gyre, I see a very different pattern. Clearly, we're not outside where we have a lot of internal variability affecting this. For example, if I just looked at a time series 87 to 2006, I would say the sink is declining. But if I just shift that a couple years, 1990 to 2009, I'd say the sink is growing. So clearly, we're having a lot of internal variability. And we wouldn't say that we're starting to see any kind of long-term response to the atmosphere that's sort of consistent at long time series. So that's what we found with the observations and has led us to the kind of a bigger scale question of, what should we really be expecting from these data? When should we be expecting to see the response of the ocean kind of consistently to the atmospheric perturbation? When should we be able to see that growing sink? When should growth in the sink actually be detectable? And we don't have observations to answer that question. And we don't really have theory to answer that question. So that has led us to turn to an Earth system model to begin to ask the question, what is the magnitude of internal variability? And when should that internal variability emerge from the force trend? So I'm going to use an Earth system model to assess detection timescales in the last part of my talk. We're using the Community Earth System model from NCAR, a great resource for everyone. And we're using this model that's been run in a really new and innovative and exciting way, which is as a large ensemble. And so many of you have probably heard of the large ensemble. Some of you probably have not. So I'll just take a few slides to explain what it is. A large ensemble is to use a single climate model with one structure and one set of forcing, but to run it many, many times, tens of times, with very small perturbations in the initialization that lead the model to take different paths through the internal variability inherent to the climate system. So essentially, the model has ENSO in different years. It has a high, one model will have a big El Nino in 1997, another will have it in 2002, another will have it in 2005. And it's just, the statistics of El Nino are the same because it's the same model, but the actual phasing is different. And so we begin to capture kind of the envelope of potential internal variability that is out there, and we can look at the effect of that internal variability on any variable that you have in your model. So this is global mean surface temperature, but we'll also look at it, for our purposes, in the CO2 flux. So to just discuss this plot a little bit more, if this is the global mean surface temperature anomaly, there was a control run done with the model up through 1850 when the forcing started. Member 1 ran until the end of 1919. And then for the initial conditions on January 1st of 1920, there was very small round-off level error, so 10 to the negative 14th level temperature anomalies in the atmospheric state of this model. And you can think of that as the butterfly that sets the individual ensemble members off on these slightly different paths. And surprisingly quickly, in a year or two, the model is on its own path of internal variability. And you can see that all of the models then over the next 180 years of forcing are following the same warming pattern, but the exact path that each one of those ensemble members is taking is slightly different. And so to think about this a little bit more, the plots from Desser et al. 2012 and Nature Climate Change really bring this point home, I think. So in what they do in that paper is they're looking at surface temperature, winter, of 55-year trend from 2005 to 2060 over the US and Canada. And so they take one of these ensemble members, one of these little gray lines, and then they take another one and say, what's the trend over 55 years? In the one that cools the least over this area and in the one that cools the most over this area. And now this is the same exact climate model with the same exact forcing in both cases. But yet look at the difference in how much Montana changes in its winter temperature between this one and this one. Here it cools by about 1 degree. Here it warms by 3 to 4 degrees in Montana. And that's not because the models are structurally different. It's just because the phasing of PDO and ENSO and other modes of variability, some of the variability which we don't even have quantified in terms of a set of acronyms or something like that, is just in a different phase. It's really fascinating how different these are. But yet if they take all of the members of this ensemble, which I believe include 40 in this paper, and they average them all up and say, what's the common response to that forcing? What's the part that's the same across all the models? That's this. That's the average trend, the force trend. And you'll see that this is like a pattern that if you saw this in a textbook, you'd say, yeah, that looks right. There's polar amplification in response to this strong RCP 8.5 forcing, more warming at the high latitudes, less at low latitudes. So any differences of the warmest ensemble member or the coldest ensemble member from this average, that's the effect of the internal variability. And this is the effect of the forcing. So the large ensemble gives us this potential to really look at those two pieces separately, which we haven't had before. And that's why I think it's so exciting. Just one more illustration I included in here is Seattle, Washington, for example, a place where a lot of people seem to want to go and retire when they stop being oceanographers. In this model, it warms about 5 degrees or so in Seattle, Washington, and in the coolest member, it doesn't warm at all. And you can see all the internal variability, right? So I think this is also a really important way when we think about communicating what climate change means to the public, the fact that the internal variability is probably larger on longer time scales than we thought in all these variables. And that's, of course, but on the globe, they're all kind of doing the same thing. All right, so let's do the same thing for CO2 flux. This is a CO2 flux in a large ensemble. This is a trend in the flux, 90 to 99, just a 10-year trend. Here's the total trend, the total amount of change over this 10-year period in 2 different ensemble members, 26 and 27. You can see that in the equatorial Pacific here, for example, the trend is for much more outgassing, and here is much less outgassing because the mean there in the equatorial Pacific is outgassing. But the very different patterns across the different ensembles. If I average across all 32 ensemble members and I look at my force trend, the common part across all ensemble members, you can see it is very, very small compared to the total trend. And that means that it's really dominated by the internal trend. Most of the total trend is made up by the internal trend for short time frames. Okay? So the internal variability is clearly dominant. And I'll show you in the next slide that most of this force trend is, in fact, not even statistically significant. So 1990 to 1999, here's that force trend where I've grayed out the part that's not statistically significant. And here, instead of showing an individual ensemble member, I'm showing the standard deviation across all members of the ensemble. And you can see how large that is. It's, of course, all in positive numbers because it's just a standard deviation. But I can do this now not just for this 10-year period. I can also do it for a 30-year period and a 100-year period here. So you can see that as time goes on, your force trend, the response to the forcing, becomes clearer and is less obscured by the internal variability. You can see that this begins to pop out. You can also see up here that there are regions, such as the subtropics, where there's really very little growth in the sink over time. And then other regions, such as the Southern Ocean, the Equatorial Pacific, and the North Atlantic, and the North Pacific, where we see much more growth in the sink. And so those are the regions where if we went out and observed, hopefully we keep observing over time, where I would expect to first see evidence for growth in the sink, where I wouldn't expect to see it in the subtropics. So the force trend is a very interesting thing to look at. And then the last thing we can do with this is directly compare this signal to noise. They have the same units. We can just compare the two and say, when does this signal emerge from this noise? From an observational standpoint, that's really what we're interested in. How long is it going to take for us to see this? And we do this with the time of emergence metric, which is simply the year when the signal to noise becomes greater than 2 and then remains greater than 2 for all future points in time. And that leads to this map. This is time of emergence, which is the year when, with this model and this large ensemble, we estimate that the sink change, the change in CO2 flux, should be detectable if we had data at that point since the year 1990. So we see the dark colors are earliest time of emergence. The yellow is at the end of the century, and white means we never see change in the sink over the 21st century. And there's a lot of structure here, a lot of structure that you can attribute to the underlying ocean circulation. So for example, we have the Southern Ocean where the sink is growing very rapidly. And even though it's a highly variable region, we do see the earliest times of emergence there in the Southern Ocean. We also do see somewhat early time of emergence in the equatorial Pacific and in some parts of the North Atlantic, but it's a very complicated pattern in the North Atlantic that's probably quite dependent on this particular model, so we'd like to really look at the Atlantic in other Earth system model large ensembles as well. The other clear pattern is the equatorial Pacific, where we do see emergence kind of mid-century. That is a region where the sink is growing, or more properly said, the efflux is declining in the equatorial Pacific. But there's also a lot of variability there that makes it harder to detect that trend. And in the subtropics, the location where we have most of our time series stations, of course, we see the latest emergence of change in the sink. That's where we're not seeing a lot of growth in the sink, as evidenced from the previous plots. And even though variability is small, it means it takes a long time for us to see any change in the sink. And in fact, many of these are where we start to see outgassing because of warming towards the end of the century. Okay, so again, my take-home messages, and I'd be happy to take any questions.
Hi, Gordon Taylor from Stony Brook. Nice talk. From some of your earlier slides, I got the impression that marginal seas were excluded from this analysis. Is that because their contribution is so trivial, or is it for want of data?
Oh, yeah. So the Lamont and Doherty database doesn't include anything where depths are less than 200 meters. So we don't even have that data in that database. And I was really excited to see that Peter is actually starting to work into the coastal zone. So it's really just a lack of data. This Earth system model, of course, has some representation, does represent those regions, but I wouldn't trust it as much as I would like to. So.
Yeah, I think it is very exciting. This emergence constraints for models is very encouraging and for future research. So how different do you think this picture would be if you had another climate model?
Yeah, a very good question. I mean, this is something I'd really love to see. Wouldn't it be great to be able to take all of our CMIP5 models and essentially make this plot and this plot by which to compare them? I mean, I would love to see it. I know that GFDL has a large ensemble. We've talked to them about trying to make some comparisons. It hasn't quite happened yet. I know one of Jorge's students is working on this. So would it be dramatically different? So I don't know why this isn't working. I think that the North Atlantic is a region where things like how much the Arctic melts, how much precipitation, where it flows through, how that circulation is, that's a region where I think it might be significantly different. I think otherwise, you might get some shifting in the timing here, but I would be surprised if it's big differences. But I'm looking forward to seeing that. Maybe in the GISS model.
We have one more? Okay. I couldn't help but notice that the North Atlantic, where it's also so important because of the large per area uptake, is the place of really interesting patterns between the Emergence Sea is one sign, the Labrador Sea is another sign, the place where the NAC, takes its right-hand turn is a third. not sign, but
Yeah.
I'm just wondering if you had a
Yeah, we've looked
physical-
into this. This is we're working on understanding that. Really what this is that there's a lot of increased freshwater flux. There's not directly melting of the Greenland ice sheet in this model, but there's a lot of precipitation falling on the ice sheet and running off. And so essentially this is a big freshwater plume, very low alkalinity, really cuts off mixed layer depths, mixing is shifting northward. And so, yeah, we're working on that analysis right now.
Thanks.
Marina, if you could come up.
Galen, I just had a quick comment. I think that, well, as you know, Keith Rogers and Tomas Froliker ran an ensemble with a GFTL model. I think the variance is quite a bit greater than with the NCAR model, if I remember correctly. The other thing is that as far as detection is concerned, Sarah has been, Schloniger, the graduate student, has been looking at different detection of different things, like the flux of CO2 is one of the things that takes longer to detect than, for example, just the CO2 concentration itself with the pH, which are and over surface DIC, which can be detected a lot more quickly.
Absolutely, yeah, because this is the derivative, not the, this is the derivative. This is the DDT of the PCO2,
Well,
which
it's
takes
the
longer.
tracer per se. You know, there's some tracers that are affected by biological processes more than others, and so they have much, much greater variability, and it takes longer to detect them than the ones that are affected.
Absolutely, that kind of a map, it varies all over the place. pH, very early emergence, NPP, very long emergence, and that's one of the great things about the large ensemble is you can look at across all these variables. Totally agree with you, yes.